All right, everybody, this is section 9.3, the integral test and the P-series. Both are really straightforward. I mean, they give you, these guidelines to use in these steps and procedures, and especially for the P-series and integral test. So it's really straightforward. The hard part is making sure you're able to take the derivative and then integrate. And so, and hopefully that's not too hard as we're moving forward. But the integral test says this. So your function has to be positive in order for you to do the integral test. It must be continuous. That means there should be no vertical asymptotes in the problem, and then it must be decreasing. And one way of determining if a function is decreasing is take its derivative, right? The derivative is a slope. If it has a negative slope, then it's decreasing. So that's what we'll be doing sometimes, taking the derivative just to see if it's decreasing. And this is for x is equal to or greater than 1. And if we have this function, we can then integrate it. And if all these are met, then both of these functions will converge or diverge depending on what the answer to the integration is. And that's the integral test. So apply the integral test to this, and you can just plug a number in there if you want, and you can see this number is going to be positive for n between 1 and infinity. No matter what number you put in between 1 and infinity, you're going to get a positive number. So we're good there. And then if we want to take the derivative of this, well, I think they do this for us. Yes, they do take the derivative. I'll actually do it because let me do it. So let's take the derivative of this. And if you might have not noticed, but if you notice, we're going to get your formula sheet. We're going to use the quotient rule. And this is F, and we're going to call this G, and the quotient rule is F prime G minus F G prime over G squared. And F is n, F prime is 1, G is n squared plus 1, G prime is 2n. So we're just going to plug that in. F prime is 1. G is n squared plus 1. F is n, and G prime is 2n, and all of this over G squared. And when we look at this, the top becomes n squared plus 1 minus 2n squared. This becomes 2n squared. N squared minus 2n squared is a negative. I'm going to write this over here. Is a negative n squared plus 1 all over n squared plus 1 squared. So if you look at this, this is the, if this whole thing was the function, we can call it whatever you want, F, this is F prime, and this is a negative. And no matter, I plug in any number between 1 and infinity, you plug any number and you're going to get a negative answer, which means the function is decreasing. It's a decrease, the slope is negative, so the function is decreasing. So that's the second So that's the second criteria. The first saying the original function is positive, and okay, I'm going to erase this now. I'll give you a second. If anybody's writing that down, I don't know, it's kind of messy, but I'll give you a second. So if we just try to go back once, the function is positive, it's continuous, and I'm going to show you that in a second, and it is decreasing. So decreasing is a derivative showing you. So now, is it continuous? Can there be anything down here that turns this into 0? And we can only use n from 1 to infinity. And no matter what number you go in there, will not turn this into 0. N squared plus 1 cannot equal 0, no matter what you put in here. I mean, you could even put negative numbers in here. It will not equal 0. So it is continuous. You know, continuous would, if something's not continuous, more than likely you see that it has some kind of vertical asymptote, and the bottom will will let you know if that's a problem there. So it meets all the criteria. So the only thing we need to do then is integrate this. And if I say u equals n squared plus 1, then du equals 2n. I need a 2 here and a 1/2 here. Now I have 1/2 du over u, and this becomes the natural log of u and the 1/2 in front. And we're integrating this from 1 to infinity. So if I put infinity in there first, and then we subtract and put 1 in there. This, what does this equal? Anyone? Natural log of 1, right? E to the 0 power equals 1. So this should be 0. I mean, you can check this out on your calculator. And here, the natural log of infinity, no matter what number you put in there, as you get closer to infinity, this increases and increases. It increases very slowly, but it does go to infinity. So this interval that we have does go to infinity, which means this function diverges. And let's see what they show. I mean, they're going to show the same thing. They show that the function, the derivative is negative. And you can test it out by putting numbers in there. By the way, I mean, I'd rather, if this was a show you work problem, I want to see the derivative. I want to see you take the derivative, because in reality, you can plug numbers in and show that this, you plug 2 in here, then you left with 2 over 5. You'll see that this is decreasing. I mean, you'll see you plug 3 in here, you end up with 3 over, you'll see it's decreasing. So you can actually plug numbers in there and show it's decreasing. I think the better way is showing that the derivative is negative that's the best way of showing that something's decreasing, and that's the more calculus way of showing it. But you can plug numbers in there. I mean, if you're doing that for a multiple choice, then you don't have to worry about showing the work. But you can plug numbers in there showing, oh, it is decreasing, so I can use that method. So the first derivative was negative for x greater than 1. Let's see what else we have. We're going to take the integration now. Yeah, they take the integration of the function. How do they get, did I miss something? No, I don't. Oh, it was, I did that. I plugged, oh, they just plug B in, but if you plug infinity here, you get infinity. How did I didn't. Did this equal 1? What am I missing? Oh, no, that was just the, I must have, now I can't remember what I wrote down because I must have wrote something down wrong. The natural log of x squared plus 1. Oh, we plugged in. I must have wrote something down wrong, but anyway, this becomes infinity. And infinity minus anything, even a very small number, becomes infinity. So I don't know how I got that wrong. What did I plug? I must have plugged the wrong number in. But anyway, since the integral goes to infinity, it does diverge. It does diverge. All right. So I don't know what I did. I'm gonna have to go back and look at the video now. There's another example I wanted to do in the book. And I just wanted to show that because there's not much here in the PowerPoint. In the book on page 610, example 2, and unfortunately you guys don't have it. I mean, you just have to look for 9.3. 9.3 example 2, because I think you guys don't have the page numbers like I do. This is the problem. 1 over n squared plus 1. And if you look at it, it's a little different from the first one. There's an X on top here. But just look at it, you plug a number in, it's positive. And if you want to plug some numbers in it, you see it's decreasing. There's nothing that will make this denominator equal to 0. So it meets all the criteria. So we're going to then integrate this. If it lets me write. And there's a rule somewhere that if you go to your sheet of 100 and you look up u squared plus a squared, where u is n and a is 1, that's one of those at the end, isn't it? Somewhere. Where is it? Maybe it's not at the end. It's I should have wrote down which one it was. Anybody see which rule it is? 1 over. Come on. There it is, number 23. So look at rule 23. And don't forget on the test, if you're going to use one of the formulas on the 100 integration sheet, make sure you write down the rules so I know what you're doing. And So this becomes A equals 1 and U equals N. This becomes 1 over A arctangent N over 1 plus C. So this becomes arctangent of N. And we're going to integrate this from 1 to infinity. And if you look at this, arctangent of 1 is, if you go and look at that, that's pi over 4, right? You look at your unit circle and find the tangent, one of those tangents that equal 1, and it's pi over 4, square root of 2 over 2 divided by square root of 2 over 2. And arctangent of infinity, you almost have to look at the graph. And honestly, I mean, you have to kind of look at this graph. I wasn't sure 100%. My trig is not that great either. I have to go back and look at my trig a lot. I haven't taught pre-calculus in a long time. So I just went to my calculator, arctangent of 200, arctangent of 500. And if you get closer and closer, you see that it's pi over 2. I mean, yeah, this is pi over 4, but it is pi over 2. And one way of doing it is just type pi over 2 on your calculator and then type in the arctangent of 500 on your calculator, and you see the two numbers match up. So this is what I get. Pi over 2 minus pi over 4 equals pi over 4.
So I learned for doing this review, e to the 99 is to infinity essentially on the calculator. So I just put arctan of negative e to the 99, it'll actually give me 90 or plus 90 for without the negative.
Oh, well, you're using degrees instead of radians.
Yeah.
Good.
And so it just tells me 90 or negative 90.
Okay, I had it for some when I did it to look at the numbers. I went to 500 and it matched up. But no, that you know what? See, it's been so long since I've done trig. I mean, since I've taught trig, I just forgot to change my my calculator to radian. I mean, to degree mode, and then you can see the answer. Good. That brings up a good point. Yeah, your calculator. If you go, if you're using the TI-84, there's a mode button where you can change it from degrees or radians. Good. So since we got a number there, this converges to pi over 4. So that we did one each, one that diverges and one that converges. But it's the same process to make sure it's continuous, make sure there's no holes in it, make sure that it's decreasing. You can look, I mean, you could, on that problem, you could have took the derivative of it, and make sure the original function is positive when you plug 1 through infinity in there, that the number is always going to stay positive or be positive. And as soon as you can do that, then you can integrate it and determine whether it's converging or diverging. If those criteria are met, then you can't do that. Use this method. P series, I think is not bad. It's really kind of simple. Here we have 1 over n to the p, and it just depends on what p is going to be. If you look in a series, P series, where p is positive constant, p equals 1, it's called a harmonic series. If p equals 1, if you put a 1 here, it's called a harmonic series. If we go to the next slide, it should tell us which one converges and which one diverges. And it shows that if p is greater than 1, And so this is all you really have to know for these P series. If P is greater than 1, this series converges. If P is between 0 and 1, it diverges. And that's really it right there. I mean, that's the key. You know, you really have to write this theorem 911 down. And I would write 910 down, the previous one that shows you, you know, you have to have decreasing, positive decreasing continuous function. Here for P series, if P is greater than 1, this will converge. That's all we want to know, that it converges. If P is between 0 and 1, which including 1, it diverges. And I really like the problem in the homework on this. That's why it's the last problem on the homework, because it makes you think a little bit. I mean, it makes you do some algebra, but makes you think a little bit. So once again, wait, did we miss anything? So for A, any harmonic series, we already said a harmonic series, for harmonic series, P equals 1. And we said if P is between 0 and 1 inclusively, it diverges. So this harmonic series, there's a 1 for each one of these. So it automatically diverges. That's all you can say. Hey, this thing diverges. For part B, they're showing you a P series of 2. And I can tell you, without even looking at the problem, if P is 2, then this is going to converge. Because if P is greater than 1, it converges automatically. So as long as we see P here greater than 1, it's going to converge. So these are nice, really quick problems. Now, they're not always that simple, and that's why I wanted to show the homework. That was it for the slides. I mean, it's that was it. But the homework, I want to go. I want to go to the last homework problem. I want to go to the P series one first. So I'm only going to do a couple of these. This might be too quick of a session. Maybe I should have did 2 sections. So this is the section I wanted a look at. I mean, question 6 without the help. And it says use theorem 911. That's the P series. And just say whether this converges or diverges. And so I want to look at the second term, 1/4 square root of 2. Now, if you look at a 4 on the outside, you can rewrite this if you wanted to. 4 is 16 times 2, right? The square root of 16 equals 4. So you can, if you bring the 4 into the square root, you have to square it. So the square root of 16 equals 4, and then we still have the times 2. So what we really have is 1 over the square root of 32. And what we really have is 1 over the square root of 2 to the 5th power. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, 5th power. And what we really have here is 1 over 2 to the 5th power to the 2nd root. This is the square root, the 2nd root. So this becomes 1 plus 1 over 2 to the 5 over 2. And then we do the same thing. If you look at this, it's 1 over 3 to the 5 over 2. If you go and do the same thing I just did for this other one, and this will be 1 over 4 to the 5 over 2. And this first one is actually 1 over 2 to the, not 1 over 2. One over 1 to the 5 over 2. So 1 over 1 to the 5 over 2 does equal 1. 1 over 2 to the 5 over 2 does equal this. So if we look at this, this is a P series. This is the n. And the P series is n to the 5 over 2. So this P is greater, 5 over 2 is greater than 1. So we know this converges. And that's all we wanted to do, is see what that fraction is. And if it's greater than 1, it's 5, the series converges, and it is. It's 2.5, it's greater than 1, so the series converges. But it's hard to see that at first until you manipulate the equations that we have here. So this is what we're looking for. And now we'll just show you, their work should be the same. Well, they didn't even show the work. Oh, well, they did. They showed that P equals 5 over 2, which is greater than 1. So this series converges. And like I said, the P series are not bad, just as long as you understand, hey, this right there, you have to turn it into something. You have to try to make it look like that, where it is a P series. And if they tell you, use theorem 911, we know we're dealing with a P series. So that wasn't too bad. I like number 6. When I looked at it, I said, hey, that's a cool problem. All right, and so there's nothing else. We can take a look at some of the rest of these. And it's the same thing. We have all these the same thing here. F is positive, you plug some numbers in here, F is positive. There's nothing between 1 and infinity that will turn this bottom into 0, so it's continuous. And you can plug some numbers in here, 2 over, if you put a 1 in there, you get 6. 2, if you put a 2 in there, you get 9. You can see this series is decreasing, or you can take the derivative of this, and you can see that series is decreasing. So once it's decreasing, then we take the integral. Once we have all 3 of those criteria met, we integrate this. U equals 3x plus 3, so du equals 3. So I'm going to bring the 2 out. And I need a du, so I'll put a 3 here and put a 3 down here. So this becomes 2/3, and when I integrate this, I get the natural log of 3x plus 3. And we're going to integrate this between 1 and infinity. And once again, you get 2/3 natural log 3 times infinity plus 3 minus natural log. And put a 1 in there, natural log of 6. It doesn't matter what this is, you're subtracting a small number. As you go to infinity here, this gets larger and larger and larger. So it approaches infinity. It just approaches infinity very slowly. If you plug some numbers in there, you see it does approach infinity, but just very, very slowly. So you get infinity, so this diverges. I think I wanted to do number. Number 3. I think number 3 was one of those that I wanted to look at. Plug a number in here, E 2.71 to the negative power. You plug any a number in there, it will stay positive. That negative just flips the E to the bottom, but it's still going to stay positive. There's nothing in here that won't make it continuous, so it is continuous. And then finally taking the derivative of E to the negative X or negative N. If you take the derivative of E to the X, it's still E to the X. But then you have to take the derivative of the U part here, and that's negative. So we put the negative out in front. So this is decreasing. It's a negative function when you take the derivative, so it's decreasing. And in a show your work, you have to show this. You have to show that all 3 of these are met. So you know, I mean, that's the key. That's why I'm showing that. You have to show that all 3 of those criteria are met. And then we're just going to integrate this. And once again, integrating that is very similar to the derivative. The integration of E to the X is still E to the X, but with a negative in front, since U is negative X, then du would just, U is negative X, du would just be -1. So we put that negative there, and when we plug this in, -1, no, we got to plug infinity first. Minus negative E to the -1. E, this approaches, look at that, negative E to the negative infinity. I think that approaches 0. If you look, I mean, it's still a negative 1 over E to the infinity. And this becomes infinity. 1 over infinity becomes 0. So this becomes 0. And this negative changes to a positive. So you're just left with 0 plus E to the -1, 0 plus 1 over E. And so this converges because it converges to a number. It does converge, converges. Good. So as long as it's going to something, it's going to converge. And that was 3. I think that was all that I wanted to show you. The rest of these, I'll post the answer key. I mean, the rest of these aren't too bad. I mean, like number 4, if you look at number 4, it says confirm the integral test can be applied to this series. So we're talking about, what is it, 9.10, or, you know, that first one. Once again, is it all numbers are positive? Is it decreasing? And you can check these out if it's decreasing. And there's no, it is continuous. There's no holes in it. And then how do you convert it to a function? And they converted it to a function for us to show you when you plug a 1 in here, you get natural log of 4 over 4. You plug a 2 in here, you get natural log of 5 over 5, and so on and so on. So you can take a look at that down there. I think that's it. Yeah, 9.10. I mean, this is once again, this is a very basic problem. You know, you have, all you're going to do is take the derivative of that, and you're going to see it's negative. It's negative, so it's decreasing. And then when you integrate it, this is what you get. And you plug infinity in there, you're going to get 0. You plug 1 in there, you're going to get it's 0 is the first part, but then you have the minus, and then you plug 1 in there, you get a negative 1/4. To the 4th. Is that it? I see, I can't even see what I just wrote over. Yeah. And we end up with, am I blind or what? Is that a, yeah, you plug 1 in here. Why did I plug a 4 in there? There's, I'm trying to get my pen. There we go. 1 to the 4th, but there's a 4 in front of it. And you end up with a positive 1/4. So it does converge to this number. And that is 9.3. I mean, it's a really simple section, I think. And right now, I mean, we're only, we're only 30 minutes, a little bit more than 30 minutes, 40 minutes into the lecture. So if I was you guys, I would go straight to the homework and finish it. See if you can go finish it. I'll post this answer key like I always do, like I have been doing. I'll post this answer key here in about 30 minutes or so. And I'll also post a video. But that's it. It's a quick, it's a really quick section. And I mean, there's just some very basic rules. You just have to take derivatives to prove that that 9.10, theorem 9.10 is good to use. Or the P series, you have to determine whether the P is between 0 and 1, which diverges, or greater than 1, which converges. And they don't even ask you what it converges to. They just want to know that P series just will tell you, is it converging or diverging? And if you look at it, it's probably, most of them are probably converging to 0 because they're decreasing functions. But you can take a look at it and see where they are converging, but they don't even ask that. All right, I think that's it. I'm going to hit stop for this recording.